Hello, my name is Matt Westerveld from Metrix CreateSpace, and I am here to present results for DARPA PA 1152, an inexpensive, practical, textile-based computing and communications platform. Our project has four main areas of focus: power storage and charging, durability, cross-garment communications, and modularity at the garment boundary. We do not focus on applications at this time. The goals of Iteration 0 are to pick our target areas of work, gather our information and materials, design, prototype, and present them to you here in this video. The primary goal of Iteration 0 was to create an electronics reference design that would be used throughout the project. It needed to have low power, communications flexibility, and be available in a small package.
So, here we are with the results of Iteration 0. The goals of Iteration 0 were fairly modest. It was to do some materials gathering as well as come up with a electronic reference design, which we've done here. We've switched from using the Atmel microcontroller to a Texas Instruments MSP430 with FRAM. This gives us lower power writes as well as upgrading to a 16-bit architecture. The power consumption, even with those two improvements, is actually much lower than the AT-Tiny. The MSP430 is currently the best in power consumption on the market that we could find, and we're very happy with the switch. The circuit that we've come up with is pretty simple. We've got 4 serial ports for communication here. We also have a boost converter, which allows us to run at lower powers than the chip even requires. The chip's operating voltage is from 2 volts to 3.6 volts. By adding the boost, we get all the way down to 0.7 volts for operation, which is really nice. In addition, we have our antenna for the inductive power and our super cap, which I'm going to discuss in a second here. We've got our initial board layout. This is a round board, and it is currently rigid. We picked round because it gives us a lot of flexibility in our design, and we like square. This is a prototype of the board. No components on it yet. We're still waiting on parts. But this was made in minutes on the protolaser using ablation, which is just amazing to us. The protolaser showed up on day 1 of Iteration 0, which is pretty funny how the timing works. But we've been doing the training, and we've mastered, I would say, FR4, which is why we went with the rigid, than the availability of the material. These test runs here, all only take a couple of minutes, so we can sort of take a look at our design right away in a physical form, which is great. We don't have to wait days or weeks. This panel actually went together in about an hour, and that gives us 16 boards with plated through holes using a conductive epoxy. So, we're going to have plenty for testing in Iteration 1. This material here is our Pyrolux. This is a flexible substrate. It's on a polyimide film, and it's very nice, but we don't have the settings quite down yet, which is fine because we've settled on the rigid board for now. So during the iteration process, we also started investigating graphene, and specifically graphene supercapacitors, which are a relatively new development. First sort of found by UCLA and now being worked on at several universities, including Rice. We've seen very, very good results. We've even seen some do-it-yourself videos on YouTube with that are non-affiliated with universities, which gives us a lot of hope. These graphene supercapacitors are simply a liquid graphene oxide solution that has been hit with a laser, so laser structured into a capacitor pattern, or in some cases a capacitor stack using an electrolyte. Our first test here, the pattern that we made didn't even make it all the way onto the to the stain that we have here, and we were able to pull around 2.5 microfarads out of it, which is extremely promising, which led us to do a little bit more investigation. The pattern that we used was just a guess, and we believe that if we pick a better pattern, we can probably get better results. We didn't even use an electrolyte on this, and we got a couple of microfarads. So we started experimenting with a larger area and a couple of different patterns. With this, we were able to get 12, 20, and even 100 microfarads with the addition of a electrolyte. The electrolyte we used, since we didn't have the right electrolyte, was actually a mixture of Elmer's glue and some rust remover, which has a high phosphoric acid content. So we definitely want to spend some more time taking a look at this, and we've come up with a concept to use this in our electronics, which is adding this to a multi-layer stack, which is, we think, a new idea based on what we've seen out there so far. There's been a lot of sort of tests in silicon, but not so much in full-blown electronics. So it's sort of experimental. It's in theory, but it's definitely an interesting thing that we're researching concurrently. If you look at the computer mock-up that we've built so far, we use an inductive antenna to charge the graphene supercapacitor, which is encased inside of the multilayer, and then it feeds the IC layer, which monitors the charge levels, and we believe this could be a possible solution to our experiment.